Hi everyone. I was originally going to call this video Intermediate, Extreme, and Uniform and discuss briefly the three fundamental theorems we're given in freshman calculus class without proof because they require results from topology as a final warm-up before we actually dive into topology. But as I was putting it together, I got carried away with Riemann integrals and advanced forms of integrals and integrability until I ended up with at least 20 minutes just on uniform continuity. So next video will be about uniform continuity and the Riemann integral and the Stieltjes integral, Lebesgue measure, and the Lebesgue integral. Very, very advanced topics in real analysis. It's all extremely cool and interesting, and all of it depends on topology. Make sure you subscribe and hit notify because the stuff about the integrals is going to be very cool. So this video and the next are another casual exploration of some interesting mathematical concepts. These are about the issues in calculus that have led us to start topology in the first place. So here's a passage from James Moncrief's book on topology. In the study of calculus, there are three basic theorems about continuous functions, and on these theorems the rest of calculus depends. They are the following. The Intermediate Value Theorem. If f from the interval a to b onto the reals is continuous, and if r is a real number between f of a and f of b, then there exists an element c inside that interval such that f of c equals r. The Extreme Value Theorem. If the function f from ab to r is continuous, then there exists an element c in a to b such that f of x is less than or equal to f of c for every x in that interval. And the Uniform Continuity Theorem, if the function f from a to b to r is continuous, then given an epsilon greater than 0, there exists a delta greater than 0 such that the distance from f of x1 to f of x2 is less than epsilon for every pair of numbers x1 and x2 inside AB for which the distance from x1 to x2 is less than delta. So these theorems are used in a number of places in introductory calculus. The Intermediate Value Theorem is used, for instance, in constructing inverse functions, such as the cubed root of x or arcsine x. And the Extreme Value Theorem is used for proving the mean value theorem for derivatives, upon which the two fundamental theorems of calculus depend. The Uniform Continuity Theorem is used, among other things, for proving that every continuous function is integrable. We have spoken of these three theorems as theorems about continuous functions, but they can also be considered as theorems about the closed interval a to b for real numbers. The theorems depend not only on the continuity of f, but also on properties of the topological space, the closed interval a to b. The property of the space of the closed interval from a to b on which the Intermediate Value Theorem depends is the property called connectedness. And the property on which the other two depend is the property called compactness. So the purpose of our study of topology is to develop these two concepts, connectedness and compactness. It's funny, the quote fundamental theorem of calculus is a specific thing, the one that connects derivation with integration. The first part says that if g of x equals the integral from a to x of f of t dt, then the derivative of g equals f. And the second part says that the integral from a to b of f of x dx equals the difference of the antiderivative at the two endpoints. So that is the fundamental theorem of calculus. But in some sense, the three theorems that we just went over are the fundamental theorems of calculus because nothing that we learn in calculus is possible without these three theorems from topology. So let's call these the three fundamental lemmas of calculus, which rest on the two fundamental concepts from topology, connectedness and compactness. So we're not going to try to prove these lemmas right now. We'll need to develop connectedness and compactness before we can prove these. Okay, so first, the Intermediate Value Theorem. So here's the Intermediate Value Theorem as it is presented to us in first year calculus. Remember, in intro calculus, the context is always real numbers. Suppose that f is continuous on a closed interval a to b, and let n be any number between f of a and f of b, where f of a does not equal f of b, then there exists a number c in the open interval ab such that f of c equals n. So the Intermediate Value Theorem states that a continuous function takes on every intermediate value between the function values of f of a and f of b. So if n is here, so notice that it could take on one value or it could take on multiple values. But the point is that no matter what n is between f of a and f of b, it's going to hit the graph of the function somewhere between a and b. So just in the context of real numbers, if we think of a continuous function as a function where the graph has no holes in it, then it's easy to believe this. So it's also true that in geometric terms, if you have f of a here and f of b here, and you draw a line between them, you're just saying that the function can't jump over the line, right? It's going to have to cross the line. So that point is, of course, what allows us to take the roots of functions, because if you have a value under y equals 0 and a value above y equals 0, then this theorem says that the graph has to cross the y-axis at some point. So let's look at an example of that. If we have 4x cubed minus 6x squared plus 3x minus 2 equals 0 between 1 and 2, the question is there a root between 1 and 2 for this equation? So what that means is we're looking for a solution to the equation, which means a number c between 1 and 2 such that f of c equals 0, right? So what we're doing is, in the theorem, we have that a equals 1, b equals 2, and f of c equals 0, so n equals 0. So all we have to do is plug in minus 1, which is less than 0, and f of 2. Okay, so one's less than 0, the other is greater than 0. So that means that we have that f of 1 is less than 0 is less than f of 2. So we know from the videos about continuity that polynomials are continuous. So if the function is continuous on an interval, then the intermediate value theorem tells us that there has to be a c such that f of c equals 0. So what this tells us is, the intermediate value theorem tells us that yes, there is a root to this equation. There's a solution to this equation between 1 and 2. And then so if we wanted to, we can use this then to figure out what the root is, to sort of arbitrary precision. Because if we calculated, we could see that the root is between 1.2 and 1.3. So we could keep doing this to arbitrary precision. So that's one example of using the intermediate value theorem. What to me is a more interesting example is that the intermediate value theorem is essential to the most basic fundamentals of real numbers, because exponential functions like f of x equals a to the x can't exist without the intermediate value theorem. The meaning of this function is constructed using the intermediate value theorem, because we know from algebra that a to the n equals a times a, where for n copies, and that if a to the minus n then equals 1 over a to the n with n a positive integer. So since a to the x raised to the y equals a raised to the x times y, we can see that if x is the inverse of a positive integer, then we'll be able to put these together so that if a raised to the 1 over n is raised to the n, that means a to the n over n, which is a to the 1, which is a. So in other words, a to the 1 over n equals the nth root of a. So then one last step, if x is any rational number, where p and q are integers and q is greater than 0, then a to the x equals a to the p over q equals the qth root of a to the p equals the qth root of a, all raised to the p. So all of this is just simple algebra. Starting with this, all of this is just unavoidable extensions of simple math using fractions and integers. But what if x is irrational? What does that even mean? From an algebraic point of view, from what we've just been doing, this is a very interesting question, because everything we've said has to do with integers and then fractions of integers. But there's no way to even interpret this, given what we just said, because this isn't a fraction. So what does it mean? It means that we're right back where we started with, once again, gaps in the rational numbers, that there are exponents that are between all rational numbers. We can't do it using what we've done here. What we do is we use the intermediate value theorem to define this value. So there are holes in the graph. If we have the graph of 2 to the x, looks like this. But of course, they're infinitely close together. So what we want to do is fill in these holes by defining f of x so that f is an increasing function. So that if it's between two rationals this way, it's going to be between two numbers this way. So for instance, with the square root of 3, the square root of 3 is between 1.7 and 8. So we need 2 raised to the square root of 3 to be between 2 raised to the 1.7 and 2 raised to the 1.8. Now this makes sense because this is the same as 2 raised to the 17 over 10, and this is 2 to the 18 over 10. You can keep doing this. You can get these numbers as close as you want to the square root of 3. We've gone over this 100 times now, and that is what we define 2 to the radical 3 to be. How do we prove that that works? It's using the intermediate value theorem. But so the important point, again, is that continuous isn't good enough. We can't just use the fact that the function is continuous. We're not even able to define the most fundamental concepts of the arithmetic of numbers without understanding sets of numbers more thoroughly than we get from the concept of continuous. When they say continuous, what they mean is continuous over the real numbers, because the real numbers have another quality, which is that they're connected. And in fact, the intermediate value theorem isn't even true if the domain of the function is not connected. And I showed you an example of that last year, that if we have a function that goes from rationals to rationals, then even the function like this, insanely, this function is continuous over its domain. Obviously it's not, because it looks like this, and then there's a gap, and then it goes up, where it's square root of 2. But the reason is because from the definition of continuous, no matter how close you get, you can always slice it thin enough that you can get a neighborhood on either side of that value. That's what continuous means. So if the function is rational to rational, the concept of continuous doesn't see this gap. It's very strange. What we really need is that the set is connected also, because that's what sort of attaches them. You can't have a break like that. So the intermediate value theorem is used all over the place. It only holds true in the context of freshman calculus because freshman calculus is over the real numbers and they're connected. Okay, next up, the extreme value theorem. So the extreme value theorem, it's all about maxima and minima. And that's the main thing that at least I remember about studying differentiation, which is that if you have a function like this, then there's some point here where the derivative is 0. In other words, there's a maximum point on this hump, right? And then a minimum point on this hump. So a function has an absolute maximum if f of c is greater than or equal to f of x for all x in D, where D is the domain of f. And it has an absolute minimum if f of c is less than or equal to f of x for all x in D. So the absolute minimum and maximum are called the extreme values of f. So notice that what I'm saying here is only the definition of absolute minimum and maximum. Some functions don't have one or the other, like y equals x squared. It doesn't have an absolute maximum because it goes up forever, right? It does have an absolute minimum at 0. But it does not have an absolute maximum. Some functions don't have either, like x to the third comes down and then it goes like that, both to minus infinity and to positive infinity. It never stops. So let's look at this function, 3x to the fourth minus 16x to the third plus 18x squared from minus 1 to 4. So it looks something like this. So the domain of the function is minus 1 to 4, and at minus 1, so it's 3 times 1 minus 16 times minus 1 plus 18 times 1. So it's 34, 37. So it has an absolute maximum at minus 1, 37. And then it has another point here at 1, 5, and one at 3, minus 27. At 1, 5, it has a local maximum. So the function has a local maximum at c, when f of c is greater than or equal to f of x, when x is near c. That means an open interval around c. Okay, so this function has a local maximum at 1 because in the area near 1, it has a maximum at 5. And similarly, a local minimum is when f of c is less than f of x when x is near c again. So it's when there's an open interval around the value, then it has a local minimum. And then so not only that, this is a local minimum, but this is also the absolute minimum of the function because 3, 1 minus 27 is as low as this gets. So it has the absolute maximum here, the absolute minimum here, and also a local minimum here. But then what about this point, which is 432? It's not an absolute maximum because the point at -1 is higher, but it's also not a local maximum. That's important to understand because a local maximum requires an open interval. But on an endpoint, there is no open interval around this because there's nothing over here to the right of it. So notice that, again, everything I'm saying here is just the definition of local maximum and absolute maximum. Nothing that I've said so far requires that a function have any of them because, like I said, y equals x to the third doesn't have, whoops, that doesn't look anything like it. Doesn't have any of them. It doesn't have a local or an absolute maximum. But this is what leads to the extreme value theorem. What are the conditions under which a function f is guaranteed to have extreme values? So this is the extreme value theorem. If f is continuous on a closed interval ab, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d inside the interval. So there are two aspects to this theorem. The first is that the function must be over a closed interval, and it's fairly easy to see why that's the case, because if we had f of x equals 1 over x, where x is greater than 0, this function is just the hyperbola like that. And if the domain is open, even if it's from 0 is less than x is less than 1, there's no maximum value here because as we get closer and closer to 0, we're never reaching a stopping point. So it's just going to keep increasing as we get closer and closer. So this function, if the domain is open, will not have a maximum value. But notice though, if we have it be a closed interval, so remember, we can't have a closed interval where 0 is less than or equal to x because 0 is not in the domain of this. But if we make the lower domain 1, then this is definitely going to have a maximum value right there. And if we make it even 0.1, then it'll still be y equals 1 over 0.1 equals 10. So it would be up here somewhere, right? And no matter how small we make this, no matter where we put the boundary of x, as long as it's closed, there will always be a maximum value. It's only if the interval is open that the extreme value theorem will fail to be true or can fail to be true. And interestingly, it's not only where the function goes up to infinity. Actually, if the interval is open, it'll fail anyway. Because even if we have the simple function y equals x, if we have an open domain, this is not going to have a maximum value because no matter how close you get to 5, it's going to be less than 5. That means that I can pick another value that's bigger than a but still less than 5. So this shows why the interval has to be closed. And then it also has to be continuous, which is maybe not necessarily obvious. Like I think it was obvious why for the intermediate value theorem it has to be continuous because otherwise you have a jump. But for the extreme value theorem, it's not necessarily so obvious why it has to be continuous. If we look at a function like this, so x squared plus 1 is the parabola moved up 1, but it stops before 1. And then this one moves the parabola over 2. So it's kind of going like this. And it's closed on 1 here. Oh, but we're only going to, I'm sorry, this isn't here because we're only going to 2. So the function is from 0 to 2, right? So this is over a closed interval. But this still doesn't have an absolute maximum value. Why? Because it's the same thing that we had up here. This is always going to increase. No matter how close the number is to 1, I'll always be able to find one that's even closer to 1 that still gives a value bigger than the one that we started with. So this function also has no absolute maximum value, not because the interval is closed, but because the function is not continuous. So both of these things, it has to be continuous and it has to be over a closed interval for the extreme value theorem to be true. But these examples, these aren't even really the problem with the extreme value theorem. There's an entirely different problem that isn't so obvious at all. So what we've been looking at are sort of like the pathological, like the obvious cases that come up in introductory calculus. But these all have to do with regular real number continuity, right? We're always assuming we're in the context of the real numbers. And this is why the extreme value theorem insists that the function be continuous over a closed interval. So we're talking about a function like this. And the extreme value theorem claims that if this is a continuous function over a closed interval, that it's going to have a highest point here. But how do we know that that's true? It's getting back to the question of continuity and the question of gaps. Would it be possible for there not to be one? Like, what if the highest point, what if this function was over the rational numbers and c was at the square root of 2? Then it would be forever getting higher without ever touching. So you could always get higher and higher. It would be sort of like the St. Louis Arch right before they put in the final piece. Here's another example. So this parabola would actually be x minus square root of 2 squared. That looks a little weird to be claiming that we're dealing with the rational numbers here, but the coefficients are real numbers. But I came up with one where this is a real issue. So the graph of this looks like this. And it comes up here at 4. But the lowest points are at the square root of 2 and minus the square root of 2. This is a polynomial that you can believe in. It just has integer coefficients. And yet, if this function is just defined over the rationals, it does not have an absolute minimum, because the point where the minimum should be is at the square root of 2. So the point is, just like with the intermediate value theorem, something more is needed here. It's not enough to say continuous, because over the rationals, this is continuous. So what is needed is the concept of compactness. So the definition of compact is a subset K of a metric space X is said to be compact if every open cover of K contains a finite subcover. So this is about as strange as topology gets, because if this is not true of your domain, then you cannot prove that every function is going to have an absolute minimum. But what is it that we require in order to prove that there is a lowest value here? We need to prove that every open cover of K contains a finite subcover? What in the world does that mean? What do those have to do with each other? That's really bizarre and really interesting, and that's what we're going to be studying for the next few weeks. So it turns out that every closed interval of real numbers is compact. That's why the interval has to be closed, and therefore the extreme value theorem is true. So when we say it's over a closed interval, it's not just these issues like this one. It's even true here, that even though this looks continuous, it doesn't look like there's any problem here, but we need to do it over a closed interval of real numbers, that is, over a compact set, or we can't prove there's an absolute minimum at all. The extreme value theorem is required to prove the mean value theorem, and the mean value theorem is required to prove the fundamental theorem of calculus. Literally, calculus falls apart without being able to prove the extreme value theorem, and we need topology, we need compactness in order to prove it. Okay, next time we'll look at the third fundamental lemma of calculus, uniform continuity, and explore the insane directions that freshman calculus can go as we get more advanced, in particular, Lebesgue measure and the Lebesgue integral. So please hit notification and come back, because the Lebesgue measure and Lebesgue integral are really cool. All right, thank you. See you next time. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.